Now we have the final presentation of this webinar, in which Mr. Shabir will show how to perform the performance-based design using ETABS.
In this presentation, so I'll be just discussing about the features that ETABS has to offer for nonlinear modeling and analysis. Um, so let's start with the modeling options first. So when we look at the types of nonlinear models that we can, and the type of nonlinearities that we can put in our mathematical model, there are different types. So we have what we called lump plasticity models, where we put the plasticity in a certain location where we expect the maximum moments to occur, or we can have like a distributed plasticity model where everything is modeled as nonlinear, right? So one idea could be where we put the hinges at the ends of the beams or the columns to model, let's say, for example, flexure nonlinear. And for shear walls, maybe we might want to model the shear wall nonlinear throughout the height in flexure, right? And so when we want to put nonlinearity in different components, then ETABS has different options to offer. Now, the list shown in this slide actually are all the nonlinearities that can be used in ETABS, and some of these can be used for both frame and area elements. So mostly your axial shear moment hinges will go to beams, either beams or columns, but mostly for beams. Axial hinges go for brace components. We have interacting and parametric PM2 M3 hinges. Mostly we model them with columns, and fiber PM3 hinge, which is basically axial and M3 moment nonlinear, which we can use to model the shear walls nonlinear, and fiber PM2 M3 can also be used to model columns nonlinear as well. So these are different options that ETABS has to offer when we want to model components as nonlinear. Now, as Mr. Ong mentioned previously in his presentation also, we have two types of components. We have deformation controlled components, and then we have uh, uh, force controlled components. Now, deformation controlled components are the ones that we model as nonlinear. Now, when it comes to nonlinear modelings in ETABS, previous slide, I showed you the list of all the nonlinear hinges that are available in ETABS. But then the other option that ETABS offers, and this is very useful for, especially for new users, is it has what we call auto hinges. And what auto hinges can help users with is that they will create the hinges automatically for you. Again, they need some input from the user. It's not like completely free and it does it all on its own. So let's say, for example, one example would be that if you wanted to model your beam as nonlinear in flexure, the minimum you would need to do is to provide the reinforcement information in the beam section. When the beam section is then assigned to the element, the program knows to pick up that beam section reinforcement and calculate the moment capacities for the hinge, right? That's only to calculate capacities. But again, because these are nonlinear components, we also need to then know what are the deformations. Now, the form that you see on the right hand side of this slide basically is asking for certain inputs, and these inputs are based on table 10-7 of ASCE 4117. And if you provide those inputs, now some inputs are automatically done. So say, for example, the row minus row dash O, if you select the current design option here, basically it takes the option, whatever the reinforcement was provided in the section. One important input would be that you would need to provide shear demand. Where does it come from? Because that table requires the shear demand as well. And if you provide these inputs correctly and then assign the hinge to the element, the program will automatically calculate the hinges for you, right? So the nonlinearity calculations you don't have to do by yourself. You only need to make sure that you provide element, section, as well as the hinge correct information. And as long as you are providing that, the hinge will be okay, and then your hinges will be calculated. Now, looking at the next slide, so these are all the different types of auto hinges that you can use in ETABS. Not only is it limited to concrete beam elements, but you can again use the same concept to model steel components, braces, steel braces, concrete columns, concrete beams, even shear walls as well, if you incline to model them as lump plasticity hinges. So these options can be used by the user to create the automatic hinges for the to be used for the nonlinear analysis. Moving ahead, another very important part is that we also need to then think about the force controlled actions. In a, let's say, for example, in a beam, we might have modeled our flexure as nonlinear, but we cannot completely ignore shear as well. Because when we are running the time histories or pushover analysis, we also need to make sure that the shear, the beam or the column doesn't fail in shear. Now, how do we do that? So one way of doing it would be to, when the analysis finishes, you extract your forces and then you check them in your spreadsheets or any other design program. But another way you can also do is to use the force controlled hinges in ETABS. Now, the force controlled hinges in ETABS, what they give you the option of is to use the reinforcement provided in the section. So say, for example, if you have a beam section, you might provide reinforcement over there. If you have a column section, you might have provided reinforcement over there. The program will calculate the reinforcement for you for that section, or calculate the capacity from that reinforcement for that section, and give you back demand to capacity ratios for that action from time history analysis. So say, for example, you might want to check beam shear. If you are provided beam shear reinforcement in the section, then the program will calculate the beam shear capacity from the section and then use that capacity to give you the DC ratio. Now, what the force control hinges allow you also to do in ETABS is basically to just ignore any nonlinearity after the forces are exceeding the capacity. So if you see the option over here, which says hinge loses all carrying capacity when the maximum load is reached, if this option is unchecked, so basically then nothing happens once the demands exceed the capacity of the section, right? And so basically they are just acting as a gauge for you, where they are measuring your demand to capacity ratio for a certain action, but they don't do anything if the demand to capacity ratio goes higher than one. They just report you back at the end of the analysis that the demand to capacity ratios are either higher than one or lower than one. And this option can be used, say, for example, if you don't model your columns as nonlinear in flexure, but you still want to check whether the column had enough PMM capacity or no, you can use the force controlled hinges to then um, get your demand to capacity ratios. And later on in the presentation also, we will also discuss performance checks, which help us basically calculate these demand to capacity ratios. So force controlled hinges can again be used in ETABS to check. So one option, one other thing you can also do is that if you check this box, hinge reduces all carrying capacity, then basically it goes into nonlinearity and doesn't have any capacity after the force exceeds when the demand exceeds the capacity. But if the option is unchecked, then this is just a demand to capacity ratio measure and not any no nonlinearity occurs. When we want to model something as nonlinear, especially in case of fiber sections require us to provide informations about fibers and also about material stress strain information as well. Now, ETABS has built-in default material stress strain for different concrete strengths, not all of them, but different concrete strengths, and also rebars and steel components. Those are default over there. But say, for example, in certain cases where your columns have confinement or your shear walls are or you are providing fiber section for a confined shear wall, you may want to use the concrete material stress strains that are confined. And ETABS allows you to calculate the confined stress strains automatically as long as you link them to a certain section which has the reinforcement information provided for confinement. Basically, what is the stirrup spacing and how many stirrups are there. So this slide, actually, you can see there are two curves. One is the black curve, which basically was the unconfined stress strain curve. And then you can see at the top, we have linked it to a frame section property here. And using the information in that frame section property, the reinforcement information, the program actually automatically calculated the confined stress strain for us. So basically, this again saves you the time of having to go back and calculate the confined stress strains by yourself if you want to provide these confined stress strains in the model for fiber sections. Now, another very good option in ETABS also is when you want to model your fiber sections for shear walls as nonlinear. What ETABS allows you to do is to provide let's say, for example, uniform reinforcement, which is the option which is shown on the left, where, let's say, for example, for vertical axial bending, you want to provide 1% uniform reinforcement. And based on that 1% uniform reinforcement, if that 1% uniform reinforcement is assigned to a particular shear wall element, the program will use that uniform reinforcement information and then calculate the fiber sections for us. In the next slide, we will see the fiber sections. Another option ETABS also has is that sometimes, and generally this is mostly true, when you do not have uniform reinforcement, but you have and confined reinforcements at the end and unconfined reinforcement in the middle, the form on the right actually then allows you to then go ahead and specify that information. What is the percentage of reinforcement at the confined end? What is the unconfined and reinforcement? And the program will use that information to not distribute the reinforcement in a fiber section uniformly, but based on the information provided for the reinforcement for that element. Now, so the steps would be: go and tell the program what is the reinforcement for a particular element, and then assign a auto hinge, and the program will use that reinforcement information and the auto hinge to create a hinge for you. So how does the hinge look like? So, so this is the option here where you can see that on the left, we are assigning a auto PM3 fiber hinge for a shear wall, right? And again, we can, if we choose to, assign the vertical axial bending only nonlinear, or we can use the general type wall where the vertical and horizontal axial bending both are nonlinear. And also, if you want to, we can also provide the shear material as nonlinear as well. Now, shear material nonlinear doesn't mean that it is flexure shear type of a behavior, but they are independent of each other. So there are some, I mean, it's not perfect, but okay, the option is still there if you wanted to model shear as nonlinear as well. If you keep shear as elastic, then program simply calculates the shear stresses for you, and then you check them against your capacity. So this is basically a typical what typical fiber section would look like, where you have concrete fibers and then rebar fibers. Now the program has calculated this automatic fiber section for us based on the information of the element. So say, for example, if this fiber section was assigned to a particular element, then the program used the information of the geometry of that element to create the concrete fibers. And then also the reinforcement information that I showed in the previous slides, use that information to assign the rebar fibers as well. If it is uniform, the reinforcement fibers will be distributed uniformly. If it was non-uniform, then it would be reinforcement will be distributed according to how the information was provided. And again, this again saves us the uh, time to basically calculate the fiber seconds for us for by ourselves. So if you go ahead and use these options, then we are saving a lot of time. So ETABS actually offers a lot of features for the users so they can quickly come up with a nonlinear mathematical model by using these automatic hinges. Again, I would emphasize again that this is not completely automatic. You still need to provide some information, but ETABS does most of the hard part. The only thing that the user has to do is to make sure that the information that it is providing to the software is correct. Another option ETABS also has is when we are modeling shear walls as nonlinear, then we want to be able to measure the strains and rotations of the shear wall. Now you might say, well, we can extract the strains and rotations from the elements, which is true. But sometimes when we have a shear wall leg, it might not be modeled as a single element, but it might be modeled as two, three elements, depending upon how you are meshing your shear wall. And then in that case, the rotations that you are getting actually are not for the entire wall leg, but for particular elements. And so what you can use in ETABS is to use gauges. Now there are two types of gauges. One what we call linear gauges, and another are quad gauges. So the linear gauges are basically line elements added from bottom of the story to the top of the story at a particular location, and they return you back average strains. So in shear walls, we expect maximum strains to occur at the end of the wall. So basically, we use or provide these strains at the ends to be able to get the strain information at the ends of the wall legs. And we use that information to judge whether the shear wall has yielded or no. Another thing we can also use is that information for is to basically judge whether we want to confine our walls more at those locations if the strains are too high. Again, if you're evaluating an existing structure, the more important part would be to evaluate rotations of the shear wall against the capacities uh, provided in ASCE 41. So you calculate the ASCE 41 provided capacities by yourself, and then use the demands from the rotation gauges. So rotation gauges basically are these pink elements here that you see, basically, which are the quad gauges. So they are four noded elements, and between those four nodes, they measure your rotation. Not only can they measure rotation, but if you are so inclined, they can also measure shear deformation, depending upon what type of a quad gauge you have selected. So you have the option. Actually, you can see here they say this is a rotation type quad gauge, but this can be changed to a shear type quad gauge as well, and they will give you pure shear deformations also. So you can use the gauges to then evaluate what is basically the rotation demands that are coming on the shear wall, and then you can evaluate them against the capacities. To get the capacities, you can always refer to the ASE 41 code, and they give you a lot of tables to provide the to calculate the capacities of the for not only shear walls but for beams and columns as well. Again, most of the hinges, automatic hinges, especially lump processing hinges, when you use the auto hinge option, the capacities are also calculated by ETABS, so you can just directly use them. So again, in ETABS, if you want to model special elements like buckling resistant braces, ETABS also got you covered for that. You can use the buckling resistant brace sections, and it also has the nonlinearity information. You can fill up these informations and then or use the default options provided by ETABS, and then use the auto BRB hinges. So this is the auto BRB hinge option here, and then the axial hinges for the buckling resistant braces can also be created. So not only is ETABS covering our typical elements, but some special elements are also covered in ETABS, like buckling restraint braces. And you can use the buckling restraint brace section and the auto buckling restraint brace hinges to model the BRBs as nonlinear as well in your tall buildings, or again, BRBs can also be used for retrofitting of existing small structures and stuff. Now, when we come, so this is all about modeling. Now, let's look at what options ETABS has to offer when we want to evaluate our results. To evaluate our results, one basic option that we will always go towards is to extract the information from the tables. Now, the tables are going to give us every information that we want, and if we want to, we can get either the envelope results, or because this will be time history analysis mostly in performance-based design, or if you are evaluating an existing structure, you will definitely want to, for some components, definitely want to extract the step-by-step results as well, which will be a better option. You can see here, they give you the options to extract forces for walls, for hinge information, like what is the rotation, what is the state of the hinge, whether it has yielded, or whether it's beyond the strength loss capacity, what is the D ratio for CP and all that. That will be checking the performance checks. But basic hinge informations, and this again, we want to use these tables to extract the information for all of the element and components, for fiber hinges, for again, as well as for lump plasticity hinges. But if you want to evaluate individual hinges, then we can go to display and then show hinge response options, and then it can plot the basic hinge for us over here. So on the left, you see the form that you see is basically showing you the result of a typical beam hinge from time history analysis. Again, if you are using fiber hinges, not only can the program give you the moment to rotation curve for a fiber hinge, but it can give you the or the state of each individual fiber in that fiber section as well. So on the right, you can see that we are uh, looking at the response of a rebar fiber in a particular column, and as to what was the amount of stress it experienced. And by looking at that, we can see that actually it did not yield also. So sometimes we are trying to look at overall results, like all the results of all the components, we will extract them from the tables. And if we find out that a certain component has some issues, and we want to go into more detail as to see what is the response of that particular hinge or a particular element, we can always go to display and hinge results option and look at the results individually and see basically what is happening, what was the capacity, how much was the demand, and why is it that the hinge has issues, right? And what again, if it is fiber hinge, you can also see the response of the fibers as well. Again, ETABS also offers the options to plot functions. Now, plot functions options can be used to plot a lot of time history results. So most of these plots would be against time. So basically the plot that you see in front of you is base shear against time, right? But again, you can also try to compare, let's say, for example, what was the shear, a particular shear was shear force against time. And you can compare that shear force to, say, for example, against the base shear to see if they are peaking at the same time. Whatever you want to use these options for, you can use these options for, right? Again, if you want to, say, for example, compare responses of two individual columns that were, for example, one is similar locations, but one is failing, one is not failing, you can again plot their forces against time as well. Because most of these plot functions, you're allowed to plot multiple plots together as well. And so the plot functions options allows you to create as many functions as you want. And a function basically is nothing, it's just a definition of what response are you plotting. And it can be, let's say, for example, a joint force, can be base shear, can be a element force, can be element deformation. Whatever you want to plot, you are allowed to plot with the plot functions options. And then you can again use these options to scrutinize your results even further if you are interested in doing that. Now, one thing that you could do again in this one, and this plot, my lines are a bit thin. I copied this plot directly from ETABS, but basically what we are looking at in this plot is what is the amount of nonlinear energy, hysteretic energy that was dissipated by different groups of elements within a nonlinear model, right? And in this one, you can see here that my girder elements actually were dissipating the highest amount of energy, hysteretic energy. And so the more energy dissipation that we see in a particular group of element, we are assuming we know that that group of element basically has a lot of nonlinearity, right? Again, you can, because these are plotted against time, you can also start to see when the energy dissipation actually starts in a particular group of elements to see whether that group of element which yielded first, whether our columns are yielding first or our girders are yielding first. So you can use these options basically to again scrutinize your results even further as well. Now, another thing you can also see is basically your cumulative energy component responses. So now, what are these? Now, this is basically what was the amount of energy dissipated by different types of energy dissipations that occurred during the time stream. So what was the contribution of hysteretic damping, which is the damping coming from the nonlinearity of the components? What was the damping contribution to the by the viscous damping, the basic damping assumptions that we provide in our mathematical model, and what was the potential in the kinetic energy? And in some cases, you might have energy errors as well. And energy error is basically the difference in your input and output energies. Normally, if you run, and we'll discuss this in the following slides as well, if you run iterative analysis, which is basically converges at the end of every step, then your energy error will be nearly zero. But if you run event-to-event strategy, then your energy error you will get some energy error in your analysis. And we will discuss this one in the further slides as well. Now, another option ETABS also offers, which I just mentioned briefly previously as well, is what we call performance checks. So what are performance checks? So performance checks basically are your demand to capacity ratios. And in this kind of performance check definition, you can, if you want to, allow to add, say, for example, 11 ground motions together. And what the program can do for you is that to use the responses from the 11 ground motions for a particular performance check and average them for you and give you one final result. So how might that work? So say, for example, you have a beam, and from 11 ground motions, a beam has a certain rotation demand, right? You want to get average demand for 11. If you add all the average ground motions in this performance check and ask the program to use the option of average, basically, if you see here, the load combination method is set to maximum, but this can be changed to be set to average also. So the program will give you the average demand for that beam. Not only can it give you average demand, but it can give you average demand to capacity ratios also, because the hinges not only have demands that are coming from the time history analysis, but they also have certain defined capacity in them. When you use the auto hinge options, the capacities are automatically defined in them. And it gives you the demand to capacity ratios for each different type of category for capacity also. So you might want to get a demand to capacity ratio for IO LSCP, you can get for each level demand to capacity ratio. And these demand to capacity ratios can be used not only in performance-based design of tall buildings. Again, you can also use the same options for the evaluation of existing structures as well, right? Now, lastly, the thing that I want to mention is about the analysis solution scheme available in ETABS. So one will be your best typical iterative analysis that ETABS has always had, where you run the analysis and it checks for convergence at the end of every time step. But you also are allowed to use event-to-event strategy. Now, event-to-event strategy, if the users are using in ETABS, they need to be a little bit careful, because event-to-event strategy actually never really checks for convergence. And that's why I said in my previous slides also, is that if you run event-to-event strategy, you might get an energy error. If your energy error is high, you should look back and maybe refine your model to reduce your energy errors. So the reason why you get energy error is because there is a difference in input and output energy. And the reason is because the event-to-event strategy actually never really checks for convergence. So when you run event-to-event strategies, you will have it's very difficult for you to have convergence issues. You will not have any convergence issues because the program doesn't do any convergence. But again, you still want to check your energy errors if you're running event-to-event strategy. So event-to-event strategies, you're allowed to run, but again, please always check for your energy errors, because event-to-event strategy does not check for any conversion, right? So yeah, so for that's all the options that I have to show for my ETABS. Now, lastly, the thing that I would like to emphasize for all the people who are interested in doing the performance-based design or evaluation of existing building structures in ETABS is that I would encourage everybody who's interested in this to go and study the API for ETABS. Now, what API for ETABS does is it allows you to connect to ETABS and then manipulate ETABS as you like. So you can extract any results that you want. You can modify the model as you like. Also run analysis. Do whatever you want to do. Whatever you can do by yourself in ETABS, the API will allow you to do. But what it will help you with is to automate a lot of the processes that you might find are very time consuming, especially in case if you are doing your performance based design, because a lot of the results would need a lot of data to be processed. So a certain result, let's say for example, we strong demonstrated that we check the foundation forces at every time step. Again, to get that information and to apply those forces into your foundation model will require you to process a lot of data, which sometimes you will struggle to do in ETABS, not because a certain person might not be able to do it, but sometimes even to process the amount of data that you're going to get in ETABS will be, or in Excel will be, it will be difficult because Excel itself will struggle to do it. So you might want to look into ETABS API, and it will help you a lot um, in expediting performance-based design, and also making your life easy by giving you uh, like ability to model your nonlinear model quickly and get the results quickly and make judgments on your results after. So rather than having to spend a lot of time processing the information that you are getting in ETABS, you can just use the API to process the results quickly, so you as an engineer can make judgment on the results, or whether your results are good, bad, or whether you want to modify something in your model to make sure that the performance is acceptable. So that's all that I have to discuss today about ETABS. So yeah, thank you.